Yeah, actually, I've made an executive decision. I didn't quite finish my handwritten slides, but at the risk of not actually talking about superconductivity, I figured I would go to the second piece, the second lecture, and I will provide the organizers with my lecture notes, and hopefully you'll be able to read the last little piece. It's actually quite nice. So I think it's quite nice. So hopefully you'll be able to read the last little piece, even if I don't quite get to it. Okay, so. Given what you've now heard about nitrogen vacancy centers as a possible quantum sensor of stuff, I'm now going to talk about a series of recent experiments and some directions that my group is putting on extremely, again, very, very pedagogical, on looking at superconductivity in superhydride materials, a topic I'm not sure whether it's in vogue within the audience, but a topic certainly, if I'd known how controversial it was going to get, I'm not sure I would have waded into it. But it is what it is, you know. One makes tasty drinks out of lemons as well. Okay, so I think there's, and I do think that in some sense, the technique that I'll show, I think in a deep way has the potential at least to answer and move the field forward in the right direction to be able to understand what's happening in these systems. Good. So actually, Nick, it was not planned, but the end of Nick's talk was absolutely perfect. He sort of emphasized, indeed, that in addition to temperature as a thermodynamic tuning parameter that you often think about, and doping perhaps as the other parameter that you think about in superconductivity, pressure can also be a useful tuning parameter. So in some very, very broad sense, the sort of uniquely interesting part of this talk at some level is that the physics will be all sort of at pretty high pressures. So instead of at the 1 to 2 gigapascal regime, which we can work in as well, it'll be at more the hundreds of gigapascals. And also, it will be about doing real space imaging of physics inside the sample chamber that's under such very high pressures. And that's the thing that's quite different about what we can do relative to other experiments. So certainly, you know, you're all very familiar, having seen Nick's talk literally about UTE2, about pressure and temperature phase diagrams and the use of pressure as a tuning parameter. And it turns out, just as a little bit of an introduction, I think perhaps this is a very simple idea, the apparatus that one uses to do tabletop high pressure experiments is something called a diamond anvil cell. People also use compression shock waves to be able to get very, very high pressures to determine things like equations of state, but those are usually at national facilities. But for tabletop experiments, you do something extremely simple, which is you use something called a diamond anvil cell. And I'll introduce a little bit of terminology. So diamond anvil cell consists of about the simplest thing that you could imagine. You take two pretty much gem-cut pieces of diamond, and you actually very, very carefully laser cut what would have been the tip. If you normally have a faceted diamond, as you can see here, the best reflection of light you get is basically from tapering this to a tip. You actually laser cut one of them, and then you align a second one sort of opposite, so they're extremely well parallel aligned with respect to each other. And then you simply imagine pressure is force over area. You naively put a sample here. This surface over here, this tip over here that's flat, is called the culet surface. These are each called diamond anvils. And then you simply squeeze. And that's basically, I mean, the diamond anvil cell is a very simple mechanical object that allows one to get to pressure. So it turns out there's a little bit more that one needs to be able to add to the diamond anvil to make it work. And the idea is that you know what happens if you put a little piece of putty between two things that you squeeze, it just goes out the side. So you have to prevent that from happening, and you do that by using something called a gasket. Very simple as well. You basically, what you have is this culet from this two pieces of the anvil, and you have essentially a cylindrical thing that holds everything in place, and this is called a gasket. And the gasket just prevents basically the material from squeezing out the sides, and it's sort of what allows you to get generally hydrostatic or, you know, spherically symmetric pressure distributions as best as you can at relatively low pressures. So I'll already jump into at some level what the goal of the talk will be, which is to discuss a new technique to be able to image magnetism, to be able to look at noise spectroscopy, to image electric fields in situ inside an anvil cell at high pressures. And this already begs a very simple challenge, which is, I think, well known in the community, which is that typically at high pressures, measuring local signals inside a diamond anvil cell is extremely difficult. We'll specifically focus on the context of local magnetic fields, but this really applies more generally than that. So one of the ways that people often measure magnetic fields of samples inside a diamond anvil cell, as far as I'm aware, is by using what are called miniature DACs, so extremely small anvil cells, and they put them inside, for example, a superconducting, a squid loop, or just generically an AC susceptibility coil, and you can do AC magnetic susceptibility measurements much like that. But the challenge, of course, is that in some sense, you're not just averaging over the entire sample, which sits in this very, very small region inside the gasket. You're actually averaging the physics over the entire anvil cell. And it's actually extremely hard to be able to make local measurements of physics that's happening inside the actual high pressure chamber. And this makes sense because that high pressure chamber is at high pressures. And so it's hard to stick something in, and it's also hard to stick something in because you have a gasket enclosure that I emphasize so that it's not very easy to be able to put a probe directly inside. So it turns out the strategy that my group utilizes and that my group sort of introduced is something that essentially combines lecture 1 with lecture 2. It's pretty obvious, I would say, in hindsight, and surprisingly obvious that nobody tried this. It took some years to get it working. But the idea is, would it be possible, for example, to try to embed an extremely shallow layer of sensors directly inside the anvil that's actually applying the pressure? And of course, you know what the sensor is going to be. In this case, it's nitrogen vacancy sensors that we try to implant just about 50 nanometers below the culet surface. And then the idea is that coming from the fact that these sensors are also optically active and that we can read out the optical spectroscopy, the idea would then to be do confocal microscopy through the backside and to be able to use these NV sensors as local measures of what's happening inside the anvil cell. And in particular, in the context of superconductivity and the Meissner effect of looking at local changes in the magnetic field. So, good. So let's talk a little bit. Yeah, please. No, so you can try to make them more flat. I don't know. I mean, so typically I think we work with anvils, as you'll hear in just a little second, that actually have a miscut relative to a particular axis that we like of about ½ degree. But I would guess that if you did like AFM on surface roughness, it'd be like nanometer scale. You can get it better by etching, but I don't think that actually etching changes the properties of the NV center that much. Good question. Yes, please. Solid. Yeah, so the idea actually, so I should have mentioned this maybe, but it's a very good question. So usually what happens is that here's the gasket basically. This is the sort of cylindrical thing that makes sure everything's contained. And usually inside the sample chamber, you have something called a pressure transmitting medium. You don't just have the sample sort of there by itself. It's maybe some type of salt or some type of gas, but then you take a sample, which is maybe a crystal of something, and you put it inside this pressure transmitting medium, and the pressure transmitting medium, together with the gasket, plays the role of trying to homogenize as best as possible the pressure that you're applying. Good, fantastic. Other questions? Yes, please.
Maybe I missed this. What's the Ruby doing?
Yeah, it's a very good question, very good question. So it turns out you see Ruby a bunch of times. So Ruby is the best known calibrant of pressure up to about 200 gigapascals. So the fluorescence line of Ruby is known, it's been characterized and calibrated extremely well how it shifts under pressure. So Ruby usually is used as actually a calibrant for pressure. Actually, in fact, you'll find that the NV center also changes under pressure. So at some level within our experiments, we don't really need the Ruby. It's sort of there more for confirmation. Because just the way the line of the NV shifts, that resonance line of the NV shifts, we can already tell the pressure. Good. Yeah, please, Nick.
Talk about that? I don't want to get
yeah.
Right. You're going to have pressure gradients in there. So
Oh yeah,
you
yeah.
have a very good idea of what they are if you have everything calculated.
Absolutely. That's right. I'll talk a little bit about that. You'll see there will be at least one slide about that. Good. Okay, so this is something that you've seen from lecture 1, but now I want to show you some real data. So I had promised that, again, the ground state of the NV center, as you are all now experts on, is a spin 1 3-level system. After you polarize using light, you have population all in the m sub s equals 0 state. And as a function of a magnetic field here represented in Gauss, you see that the magnetic field resonance line splits correspond to the Zeeman splitting of the m sub s equals plus and minus 1 states. This is essentially what I drew basically at the end of lecture 1. But it turns out that the schematic is not what we usually see in the experiment. We happened to discuss this at lunch. What you usually see in the experiment, I did just click it, but okay. What you usually see in the experiment is actually almost always 8 resonance lines instead of a pair of resonance lines. It's actually super nice that you see this. And the reason for this is it turns out that because of the tetrahedral symmetry and the fact that diamond makes 4 bonds, there are actually 4 possible orientations for the NV center. And as I had promised you, the NV center is most sensitive to magnetic fields projected along its NV axis. So you actually naturally get 4 pairs of magnetic resonance lines that correspond to these 8 lines, of course, all happening in pairs around 2.87. And these 4 lines actually immediately allow, in our experiment, for us to determine not just the magnitude, but the vector orientation of the magnetic field. It's overdetermined actually coming from these 4 lines. And it comes to the fact that we essentially know the magnetic field projection along 4 different directions, which uniquely determines it. So here's sort of a direct Zeeman spectroscopy would be sort of one way to measure magnetic fields inside an anvil cell using the NV center. Another way, which I didn't quite get to at the end of my last lecture that I was hoping to get to, is that in addition to directly looking at changes in the energy levels of the NV center as a function of Zeeman splitting, you can also do what's called noise spectroscopy. And here, the idea, again, is related to a question I think that was asked earlier, which is how long does it take after you polarize the NV center? There's some time scale in which the system returns back to thermal equilibrium, and that time scale I emphasized in the first lecture was about 10 milliseconds or so. But it turns out that that comes from ultimately interactions between the NV center spin and phonon degrees of freedom inside the diamond. But you can imagine that additional noise, additional magnetic field fluctuations can enhance that depolarization. So you can reach equilibrium faster than you would normally get if you did not have these extrinsic fluctuations. So in fact, you can imagine that perhaps when in the absence of external fluctuations, I see some time scale of a curve that returns to equilibrium, the population of the NV center returning to equilibrium corresponding to a 0 contrast on the order, I think here, of half a millisecond. But it might be possible that in the presence of certain fluctuations, that these fluctuations enhance the depolarization time or cause a shorter time scale, cause the coherence time of the system to go down, and that would be a measurement of noise. And the way I want you to think about noise is that if you have an interesting material that has some dynamic correlation function or some structure factor that knows about as z of t as z of 0, the Fourier transform of this correlation function in your material as z of t as z of 0 is exactly s of omega, and that s of omega will directly add additional noise to the NV center and can cause additional decoherence. So in addition to a very, very simple DC measurement, which is watching the change of energy splittings, you can also effectively operate the NV center in an AC sensing modality where you're sensing noise at a particular frequency s of omega. And noise, again, corresponding to a particular correlation time of fluctuations inside a material. Okay? Should be very simple. And typically, an easy frequency regime to operate in for omega is gigahertz frequency, but oftentimes one can actually operate at lower frequencies, kilohertz to megahertz, so you'd have to want the current fluctuations or the spin fluctuations in your material to be relatively low frequency relative to, I think, electronic timescales, for example. Good, so these are the 2 kind of sensing modalities that are natural for NV centers. Again, this is irrespective of if I'm inside an anvil or not, although my setting will specifically be inside the anvil. So let me start by actually, before we even get into superconductivity, let's do a very, very simple warm-up experiment. But first, Nick, back to previous.
Just a clarification. You embed, do you have orientational control, or this is, okay.
No, you don't have orientational control at all. So you don't have orientational control over the NV centers at all. Essentially, you implant nitrogen to be able to add nitrogen to the surface, and then you anneal. You heat up the system to pretty high temperatures to be able to get vacancies to bind with the nitrogen, and that process is pretty much random. So you get an equal orientation of all 4. When you grow diamond, you can be careful, and there you can get orientational control when you grow diamond, but that's not what typically is happening here.
Okay, thank you.
Good question. Okay, fantastic. Okay, so I just want to give a flavor of an experiment. Before we get to the superhydrides, I want to give a flavor of an experiment as sort of a warm-up. So it turns out that perhaps suspect it should be known to all of you that iron is one of 4 known metallic ferromagnets. It's one of 4 known ferromagnets, elemental ferromagnets at room temperature. And it turns out that as a function of pressure, it is known that iron undergoes a first-order structural phase transition at something like 10 to 15 gigapascals. And commensurate with that first-order structural phase transition is a magnetic phase transition where it goes from being a ferromagnet to a paramagnet. So in principle, let's imagine what we would expect to see doing spectroscopy inside the anvil cell using NV centers to look at this transition. So what can we do? So we can imagine that what we're doing here is I'm showing a confocal image, basically, here looking into the culet surface. So you can see the sort of scale bar of about 10 microns. And what I'm going to start at is I'm going to start by showing you a set of data that's at 20 gigapascals. So 20 gigapascals is over here. So it's in the regime where iron's already in the paramagnetic phase. Okay? And we've applied an external magnetic field of some amount. I don't remember exactly the external magnetic field strength. But the external magnetic field ends up leading to, given, again, the fact that it has a different projection on each of the 4 different NV axes, it ends up leading to 8 different resonance spectroscopy lines. But I have a Y position over here. What I'm showing you is that for every single Y position over here, it is the location, is the amount of contrast as a function of microwave frequency. So essentially what I'm doing, it's very simple. I'm taking essentially a line cut down through here, again, from up to down, since this is Y, from up to down. And for every single Y value, I'm showing you the microwave spectroscopy as a function of frequency. And at 20 gigapascals, given the external field that you apply, you can see that the lines essentially are pretty much straight. We typically call these waterfall plots. But they're essentially straight. That means that there is no local magnetism coming from the sample whatsoever. That's not so surprising because I'm at 20 gigapascals where the sample is supposed to be a ferromagnet anyways. But you can see again, it is something that goes from 0 to 30 microns. The size of the sample is maybe like a 7 micron pellet of iron, but there's nothing in terms of a local signature. And as I show a plot, and then you answer your question. And then as a function of decreasing pressure, you can see when you decrease the pressure now looking at the exact same type of plot, although using a slightly different color scheme, you can see that now, near where there is the sample, where you maybe expect there to be the sample, you actually see pretty large bendings of the line coming from the fact that the magnetic field induces essentially a dipole moment of the little pellet of iron, and that little dipole moment now gives you a local magnetic field, and that local magnetic field, when you're up here, you don't sense it, but as you get closer, it bends your magnetic resonance lines, and as you move further away, again, it looks that way. So up here, it looks like the same plot as here. Down here, it looks here. And in the middle, you see that it's bent, coming from the fact that the ferromagnet now is a little ferromagnetic dipole, but it's coming from this little pellet of iron. So just a very simple warm-up. Yeah, go ahead.
Just something small. Are you averaging across the Y or the X-axis, or are you like taking a?
No, it's a line. I think it's a line cut. I think it's literally a line cut. So it's like one specific value of X.
Okay.
And the reason is that if you were averaging, actually, there's certain regions over here where you'd expect nothing, even if you were. So I think it's just a line cut. A good but specific, a very nice specific question. And so what you can do is essentially you can just reconstruct the dipole, the actual dipole, depending on sort of whether or not the lines shift more to the right or to the left. You can see whether or not the average magnetic field is from the dipole is pointing against or with the magnetic field that you're applying. And you can literally not only use the NV center to directly measure the same type of hysteresis loop associated with the first order structural phase transition, but you can also directly image the dipole moment from the little pellet of iron in real space. Okay. But again, just at the moment, just a warm-up exercise to make sure that we can do things. Good. Just to give a little bit of a flavor, this is not going to be the focus, but just to emphasize that noise spectroscopy is something that we can also see. Another experiment that we tried just for fun is to look at, I think maybe Dunghai Lee was the one to suggest this to us. It turns out, as far as I understand, that ferromagnetism in metals is still a complicated subject, because it turns out that if I can channel this correctly, that the transport can lead to RKKY interactions between the magnetic moments, and the ordering of the magnetic moments can then change the transport, and there's some pretty complicated, self-consistent thing that one has to maybe solve, although maybe qualitatively I think it's all pretty well understood. So here we were looking at, again, a very, very well-studied thing, elemental gadolinium. And in particular, gadolinium is known to have a Curie, a paramagnet to ferromagnet transition at almost room temperature. The Curie temperature is pretty high. And as a function of pressure, it's known that the Curie temperature shifts downwards in temperature as a function of pressure. Unlike the previous first order phase transition, which was a structural phase transition, here when we go up and down in temperature, actually it looks to be a second order phase transition. There's no hysteresis that we can see from the NV measurements. And here, the real emphasis I wanted to emphasize is just that, in principle, we can see something that is not just in direct Zeeman spectroscopy, but also noise spectroscopy. So here, we're measuring what's known as the T1 time of the NV center. It is the depolarization time that was asked about a little bit before. How long does it take for the NV's polarization to decay back to the value that it has at thermal equilibrium? And at high temperatures, it's some value. But it turns out that as you decrease temperature, and in particular, as you cross the Curie transition, it turns out this depolarization time actually exhibits a transition somewhat reasonably commensurate to the transition that you see in Zeeman spectroscopy. Again, just emphasizing that you can kind of see the transition using both noise spectroscopy and Zeeman spectroscopy. Zeeman, what's happening is it's becoming a ferromagnet. The susceptibility is larger, so it's creating a field and leading to a larger splitting. Noise is much more subtle. So it turns out noise, you would naturally expect that as you order magnetically, that the amount of magnetic noise that you get decreases and that T1 should actually increase. The reason why T1 goes down here is actually coming from the presence of Johnson noise. So Johnson noise corresponds to current fluctuations, and it turns out that it's known that gadolinium has a kink in its conductivity as a function of the Curie transition. So at the Curie transition, the conductivity increases, and that leads to more Johnson noise, and via Biot-Savart, the Johnson noise leads to magnetic fluctuations that get enhanced, and that's what actually leads to a decrease in T1 across the Curie transition. So a lot of details, probably too much details. The operational story is that you can measure both direct Zeeman spectroscopy, and I promised you that there was also a way to do AC measurements. Here's an example of looking at the Curie transition, but in an AC way. Yeah, Nick, and then, sorry,
So,
sorry.
One of my takeaways from your earlier talk was that there is a time limit to your experiment, and it gets worse or it gets shorter at high temperatures. Is that true?
Yes,
Because,
yeah.
you know, at some point, T1 gets longer, or it gets long enough that you can't measure it?
Yeah, so usually I would say sort of okay, so let's be a little careful. So it's certainly true that, that as a general rule, you want T1 to be as long as possible. As you increase temperature, T1 gets shorter, and the fact that it gets shorter gives you a cutoff time on how long you can integrate for.
Yeah.
I mean, being able to integrate for as long as possible is always the best.
I would guess that your error bars would be getting long, or worse if your T1 is
I mean,
approaching your measurement time.
Yeah, exactly. That's right. So T1 long, you know, measurement time, your signal always increases as you integrate for longer. So if you can integrate for really long, that's always good. But if T1 gets shorter and shorter and shorter at higher temperatures, then you can't integrate for so long, and then it's bad. But indeed, it's
Here you're very safe.
here, here the measurements are quite sure relative to this. Exactly, that's right. Yeah, please.
So why is it necessarily that Johnson noise is the dominant source of noise in the metal? Because there's also 1 over F noise and stuff, right?
1 over F noise, Jesus. Okay, so let me think about this. 1 over F. Spin?
Generally comes from like conductance fluctuations.
Yeah, maybe. I'm not sure exactly. I'm not yet. I don't know that. It's okay. So it's a good question. So maybe I'll give 2 answers that won't fully satisfy you, but will be both true. I think it's known basically that at least for other examples of NV centers near metals and superconductors, it tends to be that Johnson noise does dominate. So I think that was sort of why we were thinking about that. And the other reason we thought it was Johnson noise was just the fact that it goes in the wrong direction relative to magnetic noise. But I don't think we ever really thought, actually I don't understand enough the 1/f really how that works microscopically or to translate that fully. So I cannot immediately say whether I believe you or not, but I don't know that we ever very seriously thought about 1/f fluctuations. Yeah, I don't, we've never looked in that frequency way. Other questions? Okay, but this was just the 2 points were basically that one, using the NV center inside basically the anvil at relatively low pressures, not so different for the pressures that Nick was showing. We basically looked at the pressure temperature phase diagram of gadolinium. Okay, so that's a little warm up. So it turns out, and this is now related to Nick's question actually, indeed actually, not only can you measure, and this was sort of something I wanted to emphasize, the rest of the talk will be about magnetic field measurements because we're talking about the Meissner effect. And it really is true that the NV center is the best at measuring magnetic fields because it's a spin. But it has a susceptibility to basically everything, electric fields, temperature, strain, stress, everything. So indeed, you can measure other things nominally with normalized sensitivity that's not as good as magnetic fields, but it's possible. So for example, here, there's a pretty cool behavior that people, actually it's really cool. So ab initio simulations of diamond actually predict that basically when you press, you actually have a cupping effect. So as you sort of compress down, what actually happens is that the anvil, literally the shape of the anvil, it cups a little bit like this. That's an over dramatization of what happens. So for anvil design, oftentimes people make little tips. They do toroidal anvils where they bevel a little bit to be able to sort of fight against that cupping at high pressures. But it's very hard to image this type of cupping behavior. But here, because we can very, very carefully apply magnetic fields in different directions, so we can isolate out effects of magnetic fields across this culet, we can actually measure directly the stress tensor, all 6 components of the stress tensor, and we can see, is there more shear? Turns out there's not very much shear, but you can literally see the cupping behavior as you go from sort of dark blue to lighter green back to dark blue, and that was sort of the first quantitative measurement of this cupping effect. A very, very mechanical effect, but again, just emphasizing that you can sense more than just magnetic fields. You basically couple to everything. Sort of depends on what you want to look at. Good. Does that help answer the question? Sweet. Okay, so now we turn to the topic at hand, exploring superconductivity and superhydrides. I suspect that some non-zero fraction of the audience will know more about both superconductivity and superhydrides than me, but I will try to make it work. So it turns out, as many of you have heard, there has been in the last 10, 15 years kind of a reasonable explosion of interest in materials that are known as superhydride materials. And these superhydride materials typically have a chemical formula that's some big rare earth element and a lot of hydrogen. So lanthanum hydride is LaH10. The thing that we're going to talk about today is cerium hydride. It's CeH9. There were other ones that may have been purported or not purported. And so it turns out that I think even from some of the stuff that Professor Trubakov mentioned, that indeed some very, very simple intuition for why you should expect high temperature superconductivity in these hydrogen-rich materials are one, that the low mass of hydrogen leads to a pretty high Debye temperature and reasonably strong electron-phonon coupling. And the idea somehow for superhydride materials, at least what I've read in the literature, is that people thought there was a chance that metallic hydrogen, which has been very, very hard and controversial to produce by itself, so just hydrogen pressurized to become a metal without any rare earth elements, that at sufficiently high pressures, it might be a superconductor that, again, because the low mass has a very high TC. But because it's really, really hard to get to those pressures literally by mechanical compression, the argument that people gave is that, well, maybe you can use chemistry and you can input these large rare earth elements and add a little bit of chemical pre-compression, and then on top of that do mechanical compression, but hopefully less, and still be able to yield relatively high temperature superconductivity, again coming from the fact that you have a low mass hydrogen. At least that's the intuition. It turns out that there has been some, this is a very small fraction, there's a lot of papers published on superhydride materials. I think there's now approximately a dozen different synthesized materials And as far as I'm aware, these are typically at very high pressure. So you can see that the axis here is non-trivial. It goes up to basically about 100 gigapascals. So there's a couple of zeros as compared to the last slide. But indeed, relative to the TCs that people have produced otherwise, these are pretty high TC materials. I should also say somewhat that I modified this slide today, that indeed this field has not been without controversy. So some non-zero number of dots that are on this have also been retracted as a function of recent times. So, and I think part of this retraction and a lot of the uncertainty surrounding this has been two things. One, to date, as far as I'm aware, there has been no, before us, simultaneous measurements of the Meissner effect and of transport on the same sample. Okay? And the reason for this is super simple. There's some very simple tension. If you want to do transport in these experiments, what you typically want is a very, very large culet, because you want to be able to put leads onto the sample. So you want a really large culet, sort of a large anvil to do these experiments. But if you want to do Meissner experiments, you want as small a DAC as possible. So you want to work with a miniature DAC, because then you're putting this inside a squid loop, and if the squid loop is averaging over the magnetic signal over a really large culet, that's not good for you. So you kind of have two opposite size tensions that you sort of want to work in to be able to do this. And partly, you know, there's been a lot of questions about Meissner data, because typically when you have AC susceptibility, you'll see that in most of the, I think it's believable, but in most of the plots that people are showing for this, you have to do background subtraction somewhat carefully. And I think, for example, this carbonaceous sulfur hydride, if you look at the raw data, I think maybe there's a signal there, but they certainly did some funky stuff when it came to subtracting backgrounds as well. So I think that there is some, you know, thing where, because you have, you know, AC susceptibility over this entire anvil geometry, and there's metallic contributions, other contributions, having to subtract is kind of painful. So what I'm hoping to show is that indeed the techniques that we're sort of trying to bring to bear will allow one to sort of, in some sense, sort of help solve and push this field in a direction where we can sort of see these things together. Good. Okay, so again, so you know the geometry. Our approach is very simple. NV center is implanted into the culet of an anvil cell. A platinum microwave wire used for microwave spectroscopy in the NV center. Transport leads that connect to a sample, so we can do simultaneous magnetometry, Meissner effect stuff, and transport measurements at the same time. Okay, so a very quick warm-up challenge for just a second. So I emphasized, you know, already in the previous slides that, in fact, it's pretty easy to do. It's reasonable to do NV measurements up to a few gigapascals. But just in the previous slide, I emphasized that to work with superconducting superhydrides, you have to be at hundreds of gigapascals at much, much larger pressures. It turns out, even within the field of NV science, it was sort of long thought that NV centers could not function above about 50 gigapascals, so well below the regime where you would have to get to for superconducting hydrides. And the reason for that is very simple. Here is a picture of the optical contrast, that is the fluorescence that you get out of the NV center as a function of pressure. And indeed, it's sort of an answer to Nick's question. As you apply pressure, you can see that the resonance line of the NV center both splits and shifts, splits and shifts, but at something like 60 or 70 gigapascals, the amount of contrast that you get relative to what you had at a few gigapascals is a fraction of a thousandth. Very, very small. And so it was sort of long thought that at some level it was very, very hard to imagine doing NV experiments at such high pressures. Making a long story very short, it turns out that at some level, in a simplistic setting, the strategy is to be careful about symmetry breaking. So normally, diamond anvils that you use are typically oriented such that they're 1-0-0 oriented. And what this means is that all four orientations of your NV centers are actually not oriented normal relative to the surface cut of the diamond. What that means is as you apply pressure, you will have a uniaxial component of that pressure along some axis that's not your NV axis, and that will break the C3V symmetry of the NV center. So what we do is actually super simple. We just use 1-1-1 cut anvils where there's one specific orientation of an NV center that is directly along the culet surface, and uniaxial pressure along that does not break the C3V symmetry at all. Yeah, Raphael?
what is the percentage of uniaxial pressure compared to the hydrostatic that you have?
That's a very, very good question. So at low pressures, I think it's probably mainly hydrostatic, but I would guess that basically at the pressures that we are getting to, the amount of hydrostatic, non-hydrostatic, maybe it's a good question for Bidren actually. Bidren, Shrin, how much is non-hydrostatic versus hydrostatic? What's the ratio?
So, at very high pressure, it depends on like the pressure medium. So even, I think most of pressure medium, at very high pressure, it's all
No, but inside the anvil, like for NVs inside the anvil, what's the ratio of hydrostatic to non-hydrostatic? About like 10% or 20%?
I think it's the amount higher than
Higher, so something actually is getting to the tens of percent level. So there's a pretty large uniaxial component. Good, but you can see basically that for 100 cut anvils with NV centers inside, at even 70, 80, 90, you see very little contrast, very little signal to noise. But for 111, even getting well above a megabar, you can get very, very good magnetic resonance spectroscopy. And so this basically allows this is sort of the workhorse that allows us to get to megabar pressures. Okay, so now let's get into, just very pedagogical, a deep description of what we do. Okay? So the material that we work with is called cerium hydride. The way it's synthesized is extremely simple. So the sample chamber is packed with ammonia borane, which is something that supplies the hydrogen. A little chunk of cerium metal is put onto the ammonia borane, and it's compressed such that hopefully sort of the 4 leads are sort of touching the cerium. And then it's taken to very high pressures, let's say about 100 gigapascals. And at 100 gigapascals, the system is laser heated to be able to catalyze the synthesis of the cerium metal together with the hydrogen from the ammonia borane into cerium hydride. The synthesis procedure, it's laser heated synthesis. It doesn't always work. My understanding from folks is that maybe if you're good and lucky, about 50% of the time. And it turns out that the laser heating that they do, it's actually kind of magical. They don't just laser heat like raster a laser spot thread everywhere. What they try to do is they try to laser heat sort of the outline that kind of touches all of these, with the feeling that if you're heating the outline, you're probably sort of heating things in the center, and you don't want to overheat things in the center, so you sort of do a little circle, and then hopefully you have enough material that seeps in everywhere to be able to sort of be a contiguous superconductor that then gives you 4-terminal resistance that drops. Okay? And it turns out, the magical thing is that with NV centers, it turns out you can actually see where they laser heated. As I said, maybe in the very beginning, one of the procedures of making NV centers in my lab is actually an annealing step. And what they do with the laser heating is they're locally annealing to very, very high temperatures. So this is a white light image before anything, just to show you where the cerium metal is oriented relative to the leads. And here is not white light at all, it's confocal microscopy fluorescence. It's 637 nanometer light, and you can see the outline of where they did the laser heating precisely because more NV centers were created there than just the NV centers that we had there in the very beginning. So you kind of see where the outline of this is. Okay? So it turns out that there's a couple samples that we worked with, and what the first thing that Xiaoli does is a super nice collaboration with Xiaoli Huang's group in Jilin University. What they do is they measure magnetoresistance, and they can see that at zero magnetic field, there's a transport transition at about, I think, 90 Kelvin or so. As you increase magnetic field, the transition temperature decreases, and this is the same thing that they see in 2 different samples, one which we call sample S1 and the other which we call sample S2. But all of this at the moment is just sort of transport signatures of superconductivity in cerium hydride, something that people had observed a couple years ago already. Okay? Good. So now what's going to happen? So I'm going to attempt to show you magnetometry using NV centers inside the anvil at about 140 gigapascal. And to do that, I'm going to start by showing you how we calibrate things. Okay? Very simple. So again, in the very beginning, I showed you that at 0 magnetic field, you should expect 1 resonance line, right? 1 resonance line. And then as you increase magnetic field, this is Zeeman split into 2 resonance lines. It turns out that at high pressures, even at 0 magnetic field, you see a split line that actually comes from the fact that non-hydrostatic stresses actually couple my plus and my minus 1 state and lead to a splitting between those states. So even at 0 magnetic field, you have a stress-induced splitting between the plus and minus 1 states, which you can, well, between coupled versions of the plus and minus 1 state, which you can see, again, in optically detected magnetic resonance spectroscopy. And then what we do is very simple. We then have a solenoid, and we apply current on that solenoid. And what you expect is, as the current is applied, the magnetic field increases. And what the magnetic field should do is it should, at some level, it should then further split these lines, sort of change the eigenstates first, but then further split those lines further and further apart. And you can see this is raw data. So at 0 magnetic field, you see the bare splitting corresponding to 2e, which is, again, a stress-induced splitting. And as you increase magnetic field, that splitting gets larger and larger and larger. If you're very careful, you'll notice that actually it looks like the very beginning of that splitting getting larger is a little bit less dramatic than the splitting getting larger at larger magnetic fields, and that's real. And that's real. So the splitting is, there's some already 2e splitting, that's this value of 100 megahertz at 0 amps or 0 magnetic field. And it turns out the additional splitting that you get from the magnetic field adds in quadrature with your initial stress-induced splitting. So then from this, you can immediately back out, given a current that you apply, what is the strength of the magnetic field that the NV center feels for that current. And that's always what we do to calibrate things. At room temperature, we increase the magnetic field, and we get a map between the current and this. And we go down to low temperatures, and it turns out this particular conversion from current to magnetic field, as long as we're far away from any samples, is exactly the same. So we know that calibration is very good. Please. Shouldn't the splittings be symmetrical? Shouldn't the splittings be symmetrical? What do you mean by that?
When we're looking at the plots of
Yeah.
the splittings, we are seeing the peaks of exactly same magnitude. And in this case, when we're looking, so the right and the left of the two.
Yeah, it turns out there's no. It turns out it was something I was saying. There's actually no reason actually for single NV centers actually that there should be no reason they're symmetric actually. Literally, it's the polarization of my microwave wire that chooses which of those I excite more efficiently. For this, it's actually a little bit more confusing why they're asymmetric, but let me just leave it at the fact that there's no expectation of the amplitude, the size of the dip on each side to be the same. Yeah, please.
I thought we should expect to see 8 features.
Ah, this is good, exactly. But now we're only using NV centers in the 111 direction. Because remember, we went to very high pressures, and at very high pressures, there's only one group of NV centers that have the uniaxial stress that doesn't break C3V, and that's the 111 group. So the moment actually you're only getting signal, all of the other NVs basically won't give a signal because there's no contrast for those. But at low pressures, indeed, you will use the 8. Exactly. Very good. Okay, so now this is going to be so much simpler than what Professor Chubukov showed, but nonetheless, let me just orient ourselves from a sensing perspective what exactly the expectation might be if you have a superconductor. Well, indeed, if you have an external magnetic field, which will always represent by H, and you ask yourself, okay, there's a superconducting, possibly superconducting sample, which is a blue circle here. And let's say my sensor is the NV center. This is nominally exactly geometry. The sensor lives in the culet, the sample somewhere below it, right? It's exactly geometry. And so you might expect that if T is greater than Tc, that the magnetic field lines just penetrate in this way, and the magnetic field that you measure from the NV center should be exactly the magnetic field that you apply. But when you actually have T below Tc, the Meissner effect tells you that you expel, there's flux expulsion. And what happens here is then directly above the superconductor, you should expect that the field that you measure from the NV center, which is B, is less than the applied field, which is H. But at the very edge of the sample, because the number of field lines has to be conserved, the field that you measure from the NV center should be larger than the external field that you apply. This would be what you would expect to happen inside the high pressure chamber if you could image things locally for the field line distribution of the Meissner effect. Again, textbook stuff that all of you know. So let's take a look at what happens here. So here is an experiment, and I'll be very careful about explaining what experiment is done. Here's an experiment where we zero field cool the system below Tc, about 90 Kelvin, and then we apply a magnetic field. And you'll see that at some region, I haven't told you where the sample has been synthesized yet. Previously, it was assumed that wherever they laser heated, that's where they synthesized the sample. Turns out that's not true. But for example, at this purple dot over here, you could see that as a function of the applied external magnetic field, as you increase the field, indeed, the NV centers exhibit a larger and larger splitting. And at this particular region, again, I haven't told you what's different about them, you find that the NV centers also exhibit a larger splitting, but the change in the splitting for the same amount of externally applied field is less than the splitting that you get for the field for the purple soft region. And it turns out that allows you in some sense to define sort of a figure of merit, what we call a suppression factor, which is very simple, which is what is the field that you measure using NV centers compared to the external field that you apply. And at the purple data point over here, at the purple region of real space, I think this line, I'm not even sure it's a fit. I think this is literally x equals y. At this purple point, you find that the magnetic field that you measure from Zeeman splitting via your NV center is exactly the same field that you apply. And it turns out at this green point over here, you measure that the magnetic field that you measure in the NV center is smaller than the external magnetic field that you apply, not inconsistent with what you would expect for a Meissner effect. There'll be more evidence. So it turns out that, I mean, for the first time, I think this means that you can do imaging, sort of diffraction-limited imaging inside the high-pressure chamber. So what we do at this stage for this experiment is we simply take different line cuts in various directions all across this sort of sample chamber. And you can basically see that, I don't remember exactly what this is, maybe this is this line cut, that for regions that are outside, basically, you'll find that delta BZ, sort of, the ratio of the field measured to the field applied is about 1. Then there's contiguous regions of suppression that typically peak, and then sort of, goes out again. And so this is consistent with us being able to really image inside the high pressure chamber and say, okay, here's where we think we see a suppression of the magnetic field measured by the NV center relative to that applied externally. And this, it turns out that, perhaps unsurprising to many of you, that the laser sensor is not making sort of a very large sample. It's making very granular things, we think, something where you have superconducting islands on the order of tens or so of microns. The separation between them is not super clear, but it's a pretty disordered and non-trivial sample. It turns out, in addition to this type of suppression, which is zero field cooling, and then, well, okay, maybe first, in addition, basically to, in addition to sort of looking at sort of real space images like that, we can also, for example, take a look at zero field cooling. Then we apply, we apply a magnetic field, and then we heat up the sample. Okay? And again, we're just looking at, for example, one particular point over here. And you see, and we're doing simultaneously measurements of both 4-terminal resistance as well as magnetometry. For us, it doesn't matter. The culet can be as big as you want to make 4-terminal resistance easy, because our sensors are basic. There's no subtraction. There's nothing, you don't need any background. Your sensors are super close relative to your sample because they're inside the culet itself. And you can see that it looks like, indeed, the location where the transition ultimately seems to end up seems to be very, very similar, maybe about 90 Kelvin or so. An interesting thing that happens is that the magnetic signature of the transition seems to happen a little bit before the transport signature of the transition happens. This might be because, I think Bert was thinking that this might be because you have a pretty inhomogeneous distribution of sample sizes, so different magnetic grains may undergo a transition before the actual whole superconducting pathway gets destroyed, but I don't know that we have a really good understanding here. But maybe one other set of experiments, I think, that at the time Bert was emphasized, so doing sort of zero field cool and applying a magnetic field, that's a statement about magnetic field suppression. But what's slightly more non-trivial but also expected is magnetic field expulsion. So you expect that as you field cool, again, I'm preaching to the choir here, I apologize. As you field cool, you expect that, above the sample, the magnetic field gets expelled, and near the sample, that magnetic field that's expelled from the center gets, out to the outsides. And again, using sort of, the shape of the sample that we have from these, different line cut measurements that we did, if you take a measurement far away, you can field cool. So now we have a magnetic field that's applied at room temperature, and then we decrease the temperature decrease the temperature. And you find that the splitting far away exhibits no change, as you sort of expect. For the 2 points that are above the superconducting sample, as far as we were able to determine, it looks like indeed there is a slight suppression of the magnetic field. I should note that the suppression of the magnetic field, the flux expulsion here, is 2 Gauss. it's about 10 times smaller than the suppression of the magnetic field that you got when you applied the magnetic field after field cooling in the first place. Again, suggesting some very, very disordered inhomogeneous system. But the really cool thing as well is that when we're at the edge of the sample, we can see maybe a little bit more than a 2 Gauss enhancement of the field at the edge of the superconducting region, again consistent with the fact that the field lines are moving somewhere outside of the sample into this region at the outside. So, so here's an example of sort of flux expulsion. Continue. So combining these two previous measurements, what we can do is we can actually do a sweep where essentially we zero field cool, apply a magnetic field, field heat, and then field cool. And in these experiments, again, this is looking for hysteresis as a function of this temperature sweep. You can see that indeed it does look like there is hysteresis on field heating and field cooling. This is the same hysteresis that we had before. It's that, when you're at zero field cooling, as you field heat, you're seeing how much field is suppressed from the zero field cooled state. And when you come back, you're seeing expulsion at the level of maybe 10 times smaller magnetic field expulsion than you had on the zero field cooled suppression. One interesting thing, again, that we don't really understand is it's kind of clear that as you go to larger and larger magnetic fields, when you do zero field cooling and go to larger magnetic field, that the sharpness of this transition seems to sharpen as you increase magnetic field. Again, we don't have really an understanding for sort of what's going on there. Sort of been trying to come up with some stuff with respect to inhomogeneous superconducting grains, but we're not sure what's going on there. So let me just try to end at least this piece of the evidence with, with a little bit of really nice local inside the high pressure chamber evidence for flux trapping. Okay? So the experiment here is we field cool the system, and then we quench the magnetic field to 0. And we can compare the splitting of the NV center in that case compared to the splitting that you get at 0 magnetic field in the first place. So if no magnetic field, if you just field cool to some temperature with no magnetic field, there's some bare splitting, and you can field cool and quench the magnetic field. And it turns out that the 0 field cooled experiment exhibits your classic 2E splitting, some maybe 100 megahertz or so. And it turns out at a temperature of about 69 Kelvin, when you field cool and then you quench the external magnetic field to 0, you can see that there's still a pronounced additional splitting of the NV center that corresponds to flux, what we think that corresponds to flux trapping inside the superconducting hydride sample. And again, these are measured locally. You can see this effect above the sample and not outside of where we think the sample is. An interesting observation, it's actually really cool, so I just want to go through sort of an understanding of this. It's just data. I'm giving an interpretation of data. I believe it's true, but let me at least give you an interpretation. So the experiment that we're doing now is not just the quench experiment. We're doing a much more systematic hysteresis experiment. So we're going to field cool, okay, and then we're going to ramp the magnetic field down to negative field values and back up to positive field values and look for hysteresis. So previously, just 2 slides before, I did hysteresis as a function of temperature. Now I'm doing field cooling, hysteresis as a function of external applied field. So you start off here, you field cool at, let's say, 100 Gauss or so to 69 Kelvin, and now you start decreasing the magnetic field. As you decrease the magnetic field, it goes down, the splitting goes down, 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 down. But at 0 magnetic field, you still see a splitting. It's not at 0, it's not measuring 0 field, and that corresponds to flux trapping. As you start changing the magnetic field so that it points in the opposite direction, you continue to get the external magnetic field measured by the NV center changing. But the idea at some level is it's almost just adding in, it's just trivially adding. Like there's some flux trapped magnetic field, and your external field has gone in the opposite direction, but that external magnetic field, which is the opposite, is just adding to the flux trapped field, not doing anything very complicated to it, and then just coming over here. And then when you go back and you increase the magnetic field, you find that there's no hysteresis whatsoever. It just looks like the flux trap field is just there for the ride, and this external magnetic field adds on to whatever flux trap field you had that your NV center is measuring. But then this confuses us quite a bit. You can see what happens when you're much closer to the transition. For all experiments done of this form, when you're closer to TC, you see something different. In particular, you still start out at 100 Gauss over here. We decrease the external magnetic field, and again, at about 0 external magnetic field, there's still flux trapping. It's now a little bit less, but it's not at 0. But then, at some point, once you increase the external magnetic field sufficiently, you actually kind of get back to the y equals x line. So it looks like for temperatures that are closer to Tc, somehow applying a large opposite magnetic field causes the flux that's trapped inside the hydride to actually disappear. And then, as you increase the magnetic field from the negative direction. Now what happens when you cross external magnetic field to basically be 0, it's still that you find that the field measured by the NV center is non-zero. And but it's now trapped in the opposite direction. But then again, as you go sufficiently to high fields in the positive direction, it again looks like the opposite flux trap field is again sort of destabilized. So the picture, at least that we have of what's happening, it's a super simple picture, is basically that at some particular magnetic field, when you field cool, you trap some flux. And the orientation of that flux, let's say, is set by whatever the orientation of the field is. Now you're at that flux, and you change the field strength lower and lower and lower. You get to 0, you still have the flux inside the hydride. You apply negative field, and the field negative cancels out a little bit with the field from the hydride, but just does stuff. At low temperatures, this just stays here. And when you come back, it just still stays there. Somehow, at higher temperatures near Tc, you still trap some flux. As you apply a field in the opposite direction, somehow this dies. And then actually, it creates a flux trap field in the opposite direction, as you come up the other way, it sort of dies again. And sort of it seems like there should be some way to explain this in a simple way, but we're not sure that we have a good understanding of what's going on here.
Is it possible you're going above HC2 at this temperature?
Oh, let me think about that. I don't think so. I don't think so. I mean, we sort of thought about. I don't have a. I mean, I should have a sharper answer for why I don't think so. I think the answer is I don't think so, and I have to think a little bit for why I don't think so. But I know that I know I've thought about that question, and the answer that I came to is I don't think so. But at the top of my head, I don't remember exactly why that is.
You should have a resistance.
A resistance kink. Sorry, say it one more time.
You should have the resistance data.
We do have the resistance. Absolutely,
Zero
absolutely, absolutely.
resistance state and what the.
Yeah, sorry. Exactly. You're always at 0 resistance. Yeah, there we go. See, perfect. Exactly. Always obvious. Yeah, exactly. Okay, good. Thanks, Nick. There's a reason you're here. Good. Okay. So, yeah.
Does the same thing happen if you zero field cool it and then apply magnetic field, or does it only happen if you field cool it?
If you zero field cool it, I think the same thing happens, except you won't have. It'll be like this. You'll zero field cool. You'll get to here. I mean, the first thing you'll do, you'll be sort of along this line, and then basically you'll sort of come back to this, and then sort of come back. But your starting point will be along that line because you're zero field cooling. But I think that after you do it, you'll do the same thing. Yeah. Okay. Yeah. Go ahead.
Can you try to extract the volume fraction from your measurement?
It's right. It's a superconductor.
Yeah.
Not yet, but now yes, basically. So it turns out that those measurements actually amazing. So it's remarkable what graduate students do. So the data in that I think was like continuously taken over like a non-zero period of time. So basically, you're doing microscopy, and actually to do these measurements, basically to really know where the region is, to make pictures like this, you essentially have to do cuts, and every single one of these cuts basically takes a day to integrate the data. So then you sort of imagine doing cuts, and if you want to take the whole sample, which is much larger than this, and be able to figure out sort of the full volume fraction, that's what you should do. I mean, that's the right thing to do, but it's actually extremely time consuming. So the right thing to do actually is what Shrin and Bidrin have been working on recently, which is just to go towards wide field microscopy. Sorry, I'm gonna take 2 more minutes, but I promise it's very simple. And the intuition is that at the moment you're doing microscopy. You have a focal spot, and what would be much easier is illuminate the whole region and pick everything on a CCD. So what we're doing here is now BISCO. I don't even know which BISCO it is, but some sort of BISCO. And you can see here's a white light image, again, of what is literally the QLIT sample, the QLIT. You can see the sample here. Here's little pieces of ruby that you can see here, and here's a platinum microwave wire that we apply microwave excitation with. And that's all labeled over here. And it turns out that, just to give you a little bit of a sense, sort of the QLIT diameter is about 350 microns, and you can see There's a little sample that's kind of stuck onto the culet. I don't know exactly the thickness, but maybe about 5 to 20 microns or so, but that's sort of the geometry that we have. And here's, I think, a really cool measurement. It's just a really cool picture. So this is white light. You can clearly see the reflection from the sample, okay? What I'm going to show you in the next slide looks very similar, but it's not white light. It is on a camera, but it is a fluorescence image, and it is a measurement of the ratio of the field measured by NV centers to the field applied. And it is resolution, it's like half a micron resolution basically across a maybe like 100 micron by 100 micron, maybe not that large, some 50 micron by 50 micron region taken in a single snapshot. At high temperature, you can see, so 1.0 corresponds to this like murky green color. You can see there's no signal of the sample. You can actually see where the rubies are actually causing the NV fluorescence to be different because the ruby fluoresces itself. Sorry?
Can you tell us for us that are best 40, what is the scale?
Yeah, it's terrible. No, yeah, this is like I yell at my students all the time for this. But there's such new data that essentially yeah, it's terrible. It's so bad. But it's such new data that I think these are pixels. They don't actually translate into anything. But I can probably give you a little bit of a sense. So Shrin and Bijun, this is about 10 microns. Is that right?
Sample is about 100 microns.
Okay, so never mind. So the sample, which is you can see here, the sample here is about 100 microns. So that gives you a sense. The color scale, sorry, okay, sorry. So this green is 1, the very yellow is about 1.5, and then very dark blue is 0.
And for Meissner, you want to get
Perfect, ideally you would want to get perfect expulsion, but whether or not it's perfect depends on lots of things, of course, whether it's granular, all.
Do you ever see perfect?
No, we never see perfect, but we see very close to perfect, actually, very close. So, but again, just to give a sense, at high temperatures above TC, you just don't see anything, right? So this just means that basically the field you measure using the MSAT is the same field as the applied. And now, as you decrease temperature, you can start to see the outline of the sample. But it's not a white light image, it's a magnetic field image. It's a locally measured magnetic field of the NV center relative to the external applied field. And as you decrease temperature, you can see this. And there's signatures that you can see. You could never know that there was a cut in the sample over here. For this, you could never know that there was a region of no superconductivity, but there is actually. In fact, there's actually 2 little chunks of superconductor, and there's actually a region over here, which you can see very clearly actually, where the interfacial region actually has enhanced field because it is literally the edge of 2 superconductors compared to basically the very strongly suppressed region over here. And just to give you a sense of raw data, I promise my last slide. Again, you cannot see anything. This is sort of an image. As we take a line cut, you can literally see this is the raw magnetic resonance pictures. The lines that you get, it's complicated what's going on here, but the lines that you get basically away from the sample are more split, and the lines that you get close to the sample are less split. And the less splitting comes from the fact that the magnetic field is suppressed by the Meissner effect. And if you do the same thing, so this is a cut at low temperature, if you do the same thing at high temperature, you see it's just exactly the same. You do not see any magnetic signature of the sample. So essentially, basically, gives you kind of a nice way to do something like sub-micron limited imaging of magnetic fields at high pressure. So again, kind of at some level, imaging magnetic fields above a sample at 0 pressure, there's better ways to do this. You can do scanning squid, there's lots of ways to do this. But I think that in the context of really working at high pressure, and if we're interested in the things for UTU2 or other things, the nickelate 327 material, I do think that there's some interesting questions that this can answer. Like one dream that I'm not sure any graduate student wants to work on in my group is really to actually feed back on a synthesis loop. Like previously, these hydrides, they had no idea where they were making the material. So there's no real control about, I do a different recipe for making the material, and I know that I made more volume fraction of superconductor or not. It's not the most beautiful project, but there's some very reasonable project which is just literally try to carefully feed back along different synthesis axes to be able to maximize the volume fraction of superconductor that you make in these high pressure synthesis. I think that will already be super important for the field if it is to survive as a field. Okay, thanks so much. Sorry I went a little bit over.